In this problem, we're gonna try to solve an exercise on linear systems with double eigenvalues. So, problem, okay, solve the following IVP. So, dx dt equal minus 2x minus y, dy dt equal x minus 4y with the initial condition x of 0 equals 1, y of 0 equals 0. So solution. So first of all, let me rewrite this as in matrix or using matrix representation. Okay, so we put capital Y equal x of t, y of t. The coefficient matrix equal A, B, C, D equal minus 2, minus 1, 1, minus 4. And therefore, the system becomes dy dt equals A times y. So the technique to solve this problem is step number one, we look for the eigenvalues of A, which will allow us to find the general solution of the linear system. Eigenvalues of A, they are found by looking at the characteristic polynomial or the characteristic equation of A. Okay, so this is lambda squared minus the trace, okay, which is minus 2 minus 4, so we add them, and then we have the determinant of A, which is minus 2 times minus 4, that's plus 8, minus 1 times minus 1 plus 1 equal 0. We have to be extremely careful. Any tiny mistakes in terms of algebra will lead to some catastrophic solutions, wrong solutions, of course. So this will give me lambda squared plus 6 lambda plus 9 equals 0, which is a perfect square. Squared equals 0. In other words, we have double with lambda equal minus 3. So we do have a double eigenvalue equal to minus 3. Step number 2, we look for the associated eigenvectors to lambda equal minus 3. So we have, because we only have lambda equal minus 3, so the eigenvector alpha beta is given by the following system, okay, which is minus, so it's A minus lambda, so it's minus 2 plus 3 alpha, plus B beta minus 1 times beta equals 0, and then the other one is C, which is 1, so it's alpha, plus D, which is minus 4 plus 3 beta equals 0. So if your calculations are correct, these two equations should reduce to the same. If they are not the same, you're going to find alpha equals 0 and beta equals 0. I mean, the same in the sense of proportionality. Huh? In other words, the two equations reduces to one equation. If these two equations do not reduce to one equation, you are going to find alpha equals 0 and beta equals 0. And this is forbidden for the eigenvector. Of course, it will lead to the trivial solution 0, 0, which is an equilibrium point for the problem anyway. But in order for us to generate the general solution, we need non-zero solutions. Y1 and Y2 to be linearly independent. Therefore, they must be non-zero solutions. So, of course, here it's obvious that we have alpha minus beta. So the two equations reduces to one equation, okay, or alpha equal beta. So your eigenvector alpha beta is equal to alpha alpha, which is alpha times 1, 1. We ignore the constant in the front because when we look for the general solution, we're going to multiply by C1 and C2, and therefore the solution, so here now, step number 3, so is we need to find y1 and y2, the two linearly independent solutions, and y1 is the straight line solution e minus 3t times the eigenvector 1, 1. So this is one solution, and we need to find y2. We are in the double case, so y2 is equal to t times y1 plus e lambda t times x0, y0. So here we know everything except x0, y0, and in order to find x0, y0, we have the system again, a minus lambda, which is minus 2 plus 3 x0, and then beta, which is minus 1, so minus y0, and now we put 1, the eigenvector, and the other one is x0 plus d, which is minus 4 plus 3y0 equals 1. So here, as you can see, if we put 0, 0, we get the eigenvector, the one that we found in step 2, but once we have the eigenvector, we put 1, 1 to find the x0, y0. This will give us the y2, the second linearly independent solution from y1. So again, the two equations should be so we get the two equations that reduces to one equation, which is x0 minus y0 equals to 1. So here we don't want to find all the x0, y0 that works. We will take y0 equals 0, which implies that x0 is equal to 1. So y2 is equal to t times y1 e minus 3t 1, 1 plus e minus 3t 1, 0. Okay, so now next step, this is step number 4, the general solution. So in this case, y, the one that describes all the solutions, is going to be c1 y1 plus c2 y2, or y equals c1 e minus 3t 1, 1 plus c2 times t times e minus 3t 1, 1 plus c2 e minus 3t 1, 0. Okay, so next, step number 5, we want to look at for the specific solution to our IVP. So we have the initial condition, we found the general form, so we just need to find y of 0. So here, if I plug t equals 0 in this equation, okay, in the general solution here, I will find c1 1, 1 plus c2 times 0, so it cancels, and then we have only c2 times e minus 3t, that gives me 1, 1, 0. Or equal to the initial condition, which is 1, 0. So this gives me c1 plus c2 equals 1, using, of course, linear algebra here. c1 plus 0 equals 0, which obviously imply c1 equals 0 and c2 equal 1. Therefore, y of t is equal to t e minus 3t times 1, 1 plus e minus 3t times 1, 0.